In this video, I'm going to talk about the relationship between the direction of velocity and the direction of acceleration. It is a question I got asked the most often by students because some people think they're in the same direction and others disagree. So let's actually do an experiment to verify this. What I have here is the smart card, and it's attached to the end stop by the string. And right now it is in the equilibrium position, which I also just call midpoint hereafter. And I'm gonna actually start the card from somewhere here, and then I'll let go, so the card will be in a periodic motion. Okay? And so it goes back and forth around the midpoint, right? And during this periodic motion, there's going to be a lot of change in velocity and acceleration so that we can see their relationship better. And we're only going to look at one period. So one period means, so it starts from here and go to the top, then come back to the starting point. So we're going to look at velocity and acceleration during this just one period. And more specifically, we're going to divide this one period into 4 quarter periods. So the first quarter is from the starting point to the midpoint. And the second quarter is from the midpoint to the top. And then the third quarter is from the top to the midpoint, back to the midpoint. The last quarter, the fourth quarter, is from the midpoint back to the starting point. So we're going to look at how the direction of velocity and acceleration change over the course of those 4 quarters. And we're actually going to use this, you see the arrow thing, it's called a vector display to actually show us the direction of velocity and acceleration. It is actually using a digital arrowhead to display the direction of either force, velocity, or acceleration, depending on which indicators, which one's indicator's light is turned on. Okay, so the direction of the arrowhead represents the direction of the variable, either force, velocity, or acceleration. And normally it designates one direction to be green, the other direction is going to be red. And in fact, it also displays the magnitude. So the number of arrowheads are representing the magnitude. All right, so we're going to look at the velocity first. So let me turn on the indicator light for the velocity. Right. So now you can see the velocity indicator light is turned on. So we're gonna display the direction of velocity. All right. So you can take a guess, and what would the direction of the velocity be during those 4 quarters? Then see if it's consistent with our vector display. All right, 3, 2, 1, go. All right, did you get it right? So in fact, velocity shouldn't be too hard. Let's take a look at the acceleration, which is a little bit more complicated. All right, so let me change it to acceleration. All right, right now you can see the indicator light for acceleration is turned on. So now it's displaying the direction of acceleration. So you can do your prediction and compare with our result. 3, 2, 1, go. All right, did you get it right? In case you didn't quite catch the vector display, let's put them side by side and use slow motion to show you. Did you get the direction of both velocity and acceleration correct for all the 4 quarters? If not, take a look at the analysis. So acceleration is equal to change in velocity divided by the time. And change in velocity is just equal to the final velocity minus the initial velocity. So by definition, the direction of acceleration is going to be in the same direction as change in velocity, but not velocity itself. Okay, since time is always positive, right? So they have the same directions according to this equation. However, can we understand this from a more physics perspective, like the underlying physical process, instead of the mathematical perspective? Of course. Let's look at an example. First, let's define the positive direction is to the right. And then there's a car going at a velocity of 5 meters per second to the right. And it's also accelerating to the right. So in the next few seconds, the car's velocity may reach 8 meters per second. And the change in velocity of the car is going to be 3 meters per second to the right, positive. And it's going to be in the same direction as acceleration. And let's say, on the other hand, if the car accelerating to the left, or in other words, decelerating, then its velocity may change to 2 meters per second. And the change in velocity is going to be 2 minus 5, which is negative 3 meters per second. And negative is going to be to the left. So the change in velocity is going to be to the left in this situation, which again is the same as the direction of acceleration. So you can see the direction of acceleration is always in the same direction of change in velocity. And now let's go back to our demo. So during the first quarter, the velocity of the cart is increasing up the slope. And that means the change in velocity is also up the slope. And correspondingly, you can see the acceleration is up the slope. And since velocity is also up the slope, they happen to have the same direction. However, in the second quarter, the cart is decelerating, so the change in velocity is down the slope. Correspondingly, acceleration is down the slope. And since the cart is traveling upwards up the slope, they are going to have different directions. And similarly, during the third quarter, the cart is accelerating down the slope, so the change in velocity is down the slope, and correspondingly the acceleration is down the slope, happens to be in the same direction as the velocity. And during the fourth quarter, the cart is decelerating, So the change in velocity is up the slope. And the acceleration is up the slope. But the cart is going down the slope. So the direction of velocity and acceleration are opposite during the fourth quarter. So all this is telling us that the direction of velocity has nothing to do with the direction of acceleration. It is the change in velocity. The direction of it is going to be in the same direction as the acceleration.